The compressor pressure test in a refrigerator, whether in household appliances or small-scale industrial refrigeration systems, constitutes a fundamental verification within the maintenance and diagnostic procedures of refrigeration equipment. This test not only allows accurate assessment of the compressor's actual condition, but also helps detect possible refrigerant leaks, verify if the gas charge is adequate, and evaluate the overall performance of the refrigeration circuit. Since the compressor is the heart of the system, any alteration in its compression capacity will directly affect the performance of the entire unit. For this reason, the pressure test becomes an essential tool for both specialized technicians and advanced users who wish to verify the operational condition of their equipment. Objective of the test and general considerations. The main purpose of this test is to ensure that the compressor performs its function of compressing the refrigerant efficiently, which is reflected in electrical, thermal, acoustic, and pressure parameters. In addition, it provides a safe and reliable method to anticipate failures that could lead to more severe breakdowns, such as damage to the electric motor, loss of internal lubrication, or deterioration of the refrigeration cycle. Checking temperature in the discharge pipe. The first method consists in observing the thermal behavior of the compressor and its discharge pipe. To do this, the system must be turned on and allowed to run for a few minutes until the compressor stabilizes its operation. Carefully, the temperature is measured on the thin discharge pipe. A compressor that is compressing correctly should raise this temperature above 60 degrees Celsius, approximately 140 degrees Fahrenheit. This thermal increase occurs because when the gas is compressed, both its pressure and temperature rise. Under these conditions, the condenser should show progressive heating, starting from the inlet with higher temperature to the outlet, where it gradually decreases. On the contrary, if the condenser remains cold or barely warm while the compressor is running, it is a clear indication that adequate pressure is not being generated, meaning that the compression process is failing. Measuring electrical consumption with the clamp meter. Another precise way to verify the condition of the compressor is by measuring electrical consumption. For this, a clamp ammeter is used, which allows measuring the current absorbed by the compressor without disconnecting any wires. Once the unit is turned on and after a few seconds of stabilization, it should be verified that the electrical consumption is close to the RLA, or rated load amps, but slightly lower than the maximum value specified by the manufacturer on the nameplate. In the case of inverter compressors, the measurement must be taken at the general power input of the unit, preferably using an extension cord for increased safety. The current consumption should remain close to the nominal value of the equipment. If the consumption is much lower than expected, it indicates that the compressor is not performing effective compression. The causes may vary: refrigerant leaks, internal mechanical problems affecting the hermeticity of the compression chamber, or even wear of moving components that reduce the efficiency of the cycle. Evaluating operating noise. The characteristic sound of the compressor also provides valuable information about its condition. A healthy compressor is distinguished by emitting a low, steady, uniform, and continuous sound during operation. Any deviation from this behavior, such as metallic noises, irregular vibrations, intermittent hums, or clicking sounds, should be interpreted as a sign of malfunction. In particular, if the compressor only hums, tries to start and quickly stops, or produces repeated clicks due to thermal protector activation, it means there is an electrical or mechanical problem preventing proper refrigeration compression. This simple yet technical observation allows anticipating possible major failures. Vibration and heat test. The physical sensation of vibration and heat is also a useful diagnostic parameter. After several minutes of continuous operation, a compressor in normal condition should vibrate slightly due to the movement of its internal components, and at the same time progressively increase its external temperature. On contrary, if after several minutes the compressor remains cold or shows only slight vibration without an increase in discharge temperature, it indicates that effective compression is not occurring. This simple yet basic verification can complement other tests and help form a more complete diagnosis. Manifold gauge test. When the equipment has a service valve, a much more accurate test can be performed using manifold gauges. In this case, simply connect the low-pressure gauge to the valve and turn on the unit. A compressor in good condition will show a decrease in pressure compared to the resting value, confirming that it is generating suction on the low-pressure side. If the equipment does not have a service valve, an access valve must be installed, which requires removing all refrigerant from the system beforehand. Before installing it, it is necessary to verify that no gas remains in the circuit, ensuring the pressure indicated on the gauge is zero. In systems using flammable refrigerants, it is highly recommended to perform a full vacuum using a vacuum pump to ensure removal of any residual gas before opening the system.
Reference pressure values for common refrigerants -20 degrees Celsius, -10 degrees Celsius. According to the pressure temperature tables of the main refrigerants used in refrigerators, the following pressure values apply under low temperature conditions. R600A, isobutane. At -20 degrees Celsius, approximately -4 degrees Fahrenheit, the gauge while the system is running should read -0.28 bar, approximately -4.2 psig. At -10 degrees Celsius, approximately 14 degrees Fahrenheit, the gauge should read 0.08 bar, approximately 1.2 psig. This refrigerant operates at extremely low pressures, which notably distinguishes it from other gases. R290, propane. At -20 degrees Celsius, approximately -4 degrees Fahrenheit, the gauge should read 2.44 bar, approximately 39.6 psig. At -10 degrees Celsius, approximately 14 degrees Fahrenheit, the gauge should read 3.45 bar, approximately 50.7 psig. This refrigerant operates at considerably higher pressures, requiring greater caution during handling. R404A. At -20 degrees Celsius, approximately -4 degrees Fahrenheit, the gauge should read 2.01 bar, approximately 29.6 psig. At -10 degrees Celsius, approximately 14 degrees Fahrenheit, the gauge should read 3.32 bar, approximately 48.8 psig. It shows typical behavior of refrigerants used in low-temperature applications, common in commercial freezers. R134A. At -20 degrees Celsius, approximately -4 degrees Fahrenheit, the gauge should read 0.32 bar, approximately 4.7 psig. At -10 degrees Celsius, approximately 14 degrees Fahrenheit, the gauge should read 1 bar, approximately 14.7 psig. It falls within an intermediate pressure range and is widely used in domestic and automotive refrigeration. Procedure: compression, discharge test, and complementary tests. 1. Discharge test, main test. With the compressor off, connect the red high hose of the manifold gauge set to the compressor's discharge port and ensure the connection is secure. Make sure the high side valve on the gauge manifold is closed. Verify that the installation can withstand the test pressure and that all personnel are at a safe distance. Turn on the compressor and observe the high-pressure gauge needle. It should rise continuously and smoothly, without vibration. Increase pressure to the target value according to the refrigerant, for example 400 psig for R134A, 200 psig for R600A. Once the target pressure is reached, turn the compressor off immediately. Observe the gauge after turning it off. Remains stable or drops very slowly. Compressor in good condition. Seals or valves okay. Drops moderately or quickly. Indicates leaks or sealing defects. Compressor in poor condition. Replace. Vibrations during pressure rise. Internal valve leakage. Sealing problem. Fails to reach target pressure and stalls. For example, stays at 200 to 250 psig when 400 was expected. Degraded compressor. Stop test. Safe depressurization. Carefully open the high side valve slightly to release pressure to a safe level. Do so with protection and at a safe distance. Ensure the pressure reads 0 psig before handling or disconnecting. Suction, vacuum test, complementary test. Confirm the observations from the discharge test. Connect the blue low hose to the compressor suction port and verify that the discharge port is sealed or open depending on setup. Close the low side valve before starting. Turn on the compressor and observe the low pressure gauge needle. It should move continuously and smoothly toward vacuum. Objective is to reach approximately minus 29 inches of mercury vacuum. When reaching minus 29 inches of mercury, turn the compressor off and observe. Remain stable or rises very slowly, compressor has good sealing. Rises quickly, valve leaks or sealing problems, deteriorated compressor. Fails to reach minus 29 inches of mercury, stops at minus 14, minus 15 inches of mercury, insufficient compression. Interpretation and decision criteria. Good compression, reaches target discharge pressure and minus 29 inches of mercury vacuum, reading stable after stopping, slow rise or stable. Fair condition, partially reaches targets but shows slow or medium pressure loss or vibration, possible early valve failure, monitor or plan replacement. Poor condition, fails to reach targets, gauge needle vibrates, rapid pressure or vacuum drop after shutdown. Replacement recommended.